Thanks everyone for joining us. We're just going to have a quick run through and an introduction to those of you that are not familiar with Spectrum Centre. So who are we and what do we do? Spectrum Centre, we're spectrum management specialists. Spectrum E is our flagship radio planning tool. It's an off-the-shelf COTS SASH solution which incorporates three key modules: e-licensing, remote measurement and technical analysis. In addition, we offer consultancy services across a broad spectrum of technologies and markets, whether that's coexistence studies, interference studies, or even analysis of drive test studies to identify not spots. The scope of our consultancy work is quite broad. As I explained, our main platform and the tool that will be demonstrated today is Spectrum E, and it's a browser-based application. It features, like I said, three key modules: e-licensing, technical analysis, and remote monitoring. The demo that's going to follow today, and that will be shown by Ross, does outline some of those key benefits of that solution in terms of broadcast features. And it's worth noting that actually we have a far richer set of features that the tool offers. And we can cover these either in future events, or we can have them on one-to-one demonstrations if there's something you'd like to hear about. So just a quick look a little more closely at Spectrum E in terms of key drivers and benefits of this new solution. Simplicity of the interactions with the software. So the user interface and workflows are easy to use. In terms of performance, the speed of the calculations are far improved on previous legacy products. We've eliminated the need for onerous training, which has a knock-on effect, of course, on your training budgets. Feedback from users, and we do use that, and it's integrated back into our software, is the application is easy to use. The adoption and migration of the software from legacy products have short lead times. Okay, so just in terms of the application features, for those of you who are not familiar, just a very quick run through. Like I said, browser-based, it's supported by a mobile or on a laptop or PC or across different platforms, including Mac and Windows. The software can be used in the cloud as a SaaS solution, or it can be used on a local install. It's HTML5 compliant and can be used as an intranet style manner or a standalone mode. I'm going to hand over now to Ross, and he's going to make a start with the presentations. Over to you, Ross.
Hi, thanks very much, Sarah, for the introduction. And we'll get started. Just a quick run through of the programme that we're going to cover today. So I've got a couple of topics looking to share. Initially, we'll look at a bit of a high-level background into radio broadcast planning, specifically with single frequency networks, or SFN. Give you a bit of a background to some of the terminology, some of the technology, and then look at a summary of some of the broadcast functions that will be shown in the product demonstration after that. We'll finish up just with questions and answers. If any questions come through, we'll handle them at the end. So kick off with a brief introduction to what is a single frequency network. So single frequency network is a network of transmitters for broadcast that all use the same frequency. Because they all use the same frequency, they must be synchronized. So they're sending out and transmitting the same data across all the transmitters. So what benefits does this bring? One of the main benefits is to do with the increased frequency efficiency. So being able to utilize one channel to serve an area. So this can be a small area, maybe an infill of a city or town, and it can SFNs can be deployed into as national networks as well. Because we have multiple transmitters transmitting the same bit stream, it means that the field strength variation for our receivers is reduced. Our decoders within the receivers are able to take the multiple signals, and as long as the system has been set up correctly, we'll be able to decode and use the multiple signals for the reception. So SFNs can be deployed as standalone, or they can be deployed as part of a hybrid network with a multi-frequency network as well. So maybe using MFN for your kind of national areas, and then really drilling down, and some of the infill can be done with SFN, or there's multiple ways that these can be rolled out. Certainly, in my experience, the ITU has a vast amount of documentation, and again, there's several different technologies within these broadcast networks in terms of DVB, DVB-T, T2, ISDB, and various other technologies that can be implemented. So each of the technologies have their own parameters that are used. For this example that we'll be going through today, we're going to use quite a generic example just to show the main functionality and how we can prepare and create a network. So we'll do that by running through a broadcast engineering workflow example. And the first thing that we'll have to do within our test environment is prepare it. So what we'll do is I'll show you a couple of different ways that through Spectrum E we can import data, whether that be sites, antennas, and other parameters. We'll import from our data stores or databases that are connected using the interface within Spectrum E. We'll import from a CSV file. So if you've already got a list of stations, we'll show you how to import that, and also some of the other interfaces to other web services or databases through our API that are integrated. We'll then look at the beginnings of the network planning stage, so identifying suitable site locations using what's called the K-means algorithm. So this is taken from mobile and cellular planning, and we've implemented it to automate the way that we can identify suitable site locations. We'll look at coverage studies and how to marry up the coverage that we've created with a population, with population vector files, whether it's point data or polygon data, and identify the percentage covered that we have. So then finally, we'll have a look at the interference and how we can mitigate the interference within a single frequency network. So briefly run through the functions that we'll be using today at a high level, and then we'll get straight into the demo after that. So the K-means algorithm is used to build up from the population data, the population points that we put into the tool. It will build up clusters and then identify the best location to put a transmitter within those clusters. So previously, broadcast planning has been carried out using a grid type, maybe hexagonal grid, sort of cells to place transmitters in, but this doesn't really take into account the population density and the population distribution around where we want coverage. So this way allows us to find a better location to start our planning with. Once we've initially used the K-means algorithm, which just looks at the population distribution, clusters the population points together, and then identifies the best location. So it doesn't take into account the terrain, it doesn't take into account the propagation characteristics between the points, it just looks at the distance and creates clusters within a set distance criteria, and then puts our transmitter within that as well. So I'll introduce the algorithm and show you how that's used within our demonstration. We'll look at some of the coverage studies within Spectrum E, and again, the main advantages of Spectrum E, we have an easy way to have reproducible results. Every time you run the calculation, you'll get the same results. The inputs are to the propagation models are simple. The simulation performance, we'll touch on that when we get to the demonstration, but we'll see the speed of the calculations, how long it takes to run, and how this makes your team more productive by being able to iterate over different designs quite quickly. The transparency within the implementation of the propagation models as well. So all our propagation models, certainly our next webinar touches on one of the propagation models, the ITU 1812 model, and how that's implemented, obviously based on the recommendations and implemented into the software. So with the SFN, just briefly, we'll look at some of the parameters that we'll be looking at when we're creating our SFN interference map within the tool. So SFN networks introduce what's called a guard band. That is an additional time that allows synchronization between reflected paths and maybe a direct path, and it allows the receivers to be able to decode the signal at that point. So depending on the throughput that you require from the system, your carrier to noise ratio will change, and also depending on the type of system that you're creating, whether it's a small kind of sort of semi-localized sort of regional network, or whether it's a national network, will depend on the parameters that you use. And again, for each technology, specific to that technology, there'll be specific symbol times, guard bands, and the other parameters that we'll need for designing our network. So again, that's another part. And as I said earlier, we're not doing a deep dive into the technology, a specific technology. We're trying to keep this generic and show the functionality of the tool. So we'll move on and start the demonstration. And kick off here. So what we've got just now is Spectrum E. We're running it from the browser. And what we'll do is we'll just log in to kick off. So the first thing that we want to do, that we're interested in trying, is importing some sites. So we've got a couple of ways that we can import sites. The first way I'll show you is via the API functionality and the connections to various databases that we've created. So start this off with this test point over in the United States. Go to network, find this point here. What we can do is we've integrated with the FCC private LAN or LAN mobile database. We can click on our test station, click on the import from FCC. It will automatically populate with our station latitude and longitude. We can choose the data source that we're connecting to. Click the search radius and the specific frequency band that we're interested in, or specific frequency. So we'll go from 150 to 160 megahertz. And what we can now do is very quickly import our existing site database. It could be an existing network, and we can import that. And within a couple of seconds, we'll have that data imported with the parameters for each station here. So we can see as we scroll along, we've imported the parameters and any information that sits within that database. We can see the power. So what that is 18,000 stations, or just about 19,000 stations, very quickly imported, and where we can start our network planning from. If we go to map that object, we'll be able to see on the interface how Spectrum E handles that number of stations. So you can see there's no real difference in performance as we scroll about. And that's a very one of the ways that we can connect either via an integration with an external database, and we can also import stations using our API and pull them in from an existing database. So our next method of importing sites, what we're going to do is we're going to zoom to this area down here in Bristol. We'll just change the display, turn these subscribers off, and what we can have a look at now is some of the database and data store functionality. So what we're interested in doing is understanding around this area, is there a network that we can maybe import some sites from and from an existing database. So the data store functionality that we have in Spectrum E, we have the ability to link up with any external database. And what we can do here is, for this example, we'll use the ITU Brific. So this contains a lot of the terrestrial assignments throughout the world. We can easily filter this. So here we have 300,000 records. And what we want to do is narrow down our search. We can do that by putting a latitude, a longitude in, and then a search radius. We can see how many sites are around about that location. We can then search by specific country, if we know the site name, or we can search by frequency. So we can search for a frequency range. So let's have a look at the UHF band. 862. Again, whittling down those records till we've got 200. Again, we can even go to a specific frequency. So I'll go 578. We'll take this site here just for our example and showing how to import. So any stage through that process, we could select all the records and send them to the map. So that's what we'll do just now. We'll just send this as a generic radio object. We can see it's imported directly to the map. So this could happen with one station, or it could happen with 100 stations, up to a national network. So that's another one of the methods that we can quickly import some data to our project. So for this example, I've prepared some vector layers that we'll be looking to use, and I'll just turn these on just now. To upload specific vector layers, we support shape files and KML files. As long as they're in the correct projection, those can be uploaded. So what we've now done is imported those population points and turned on the display with the polygon and the population points here. So to use our k-means algorithm, the first thing that we have to do is place some sites down. So I'll show you another method for importing sites within Spectrum E. So if we go up to our network, we can scroll down to the bottom and import CSV file. So earlier on, we've prepared a CSV file just with the information about what we're going to import. Got that here. We'll import that, and I'll add an additional 3 stations to our project, and we'll just view these on the map to see where they've been located. So as you can see, they're in the corners of the polygon. It's maybe not the best sites to start planning a radio network for. And what we want to do is now use the k-means algorithm to identify the best locations based around these population points as the best place to put the transmitters. So we'll go back to our network. So from here, we can have a look at the various parameters that we've imported. So we've got quite relatively low antenna heights compared to the other station. We're all operating in the same frequency as well. But we can add and edit and change the specific parameters of that site. just go by going to Add Edit Object, and here we can see the detail of the parameters. So within the documentation in the Home taskbar, we've got our user manuals, so that contains more information about how we set up and how we utilize some of these functions as well. So the first thing I'm going to do is use the k-means algorithm to identify the best locations for these 3 new stations I've added to the map. So we'll highlight them first and then press k-means. It'll ask us what size of clusters do we want to create when we're identifying the best locations for these sites. We'll press create clusters, and that will run the process. And when we're viewing the map now, we can see that those 3 stations have moved to better locations to start our radio network planning. So we can see that the station 1's gone around the biggest cluster, certainly around the main population distribution within the region. Again, station 2 looks like it's trying to cover this cluster, and station 2 covered this one on the west side of the population point. So using the k-means as a way to quickly, rather than just going by a grid, we can identify better starting positions for our sites. The next stages as we plan and design the network in greater detail would be to understand what coverage are these station positions going to provide to us for our network. And then what we want to do is minimize and adjust the guard intervals and useful symbol lengths depending for our single frequency network as well. So the first thing that we'll do is calculate the coverage from these sites and to understand if there's any sites that we could move about to get into a better position to cover the population distribution. So we'll go back to our network page. We'll select all the sites. So here, what we want to do is run what's called a path loss matrix to create the coverage calculation. We'll do that using the ITU 1812 model. We'll set our standard parameters, and we'll go out 100 kilometers from each of these sites. Leave the parameters and use our profile sampling to 2000. So that roughly equates to a 50-meter terrain grid. So 50-meter grid squares along the calculation that we're carrying out. So as we run this, we can see the parallel processing of those 4 stations. So rather than going sequentially one by one through the stations, we're able to process those in parallel, so we don't have to wait. Effectively 4 times as long for all the stations to be calculated. So there we can see we've calculated the path loss matrices. And what we'll do is just click on the stations that we're interested in and viewing the coverage. And we'll create a talk out field strength received map. So we can either select the stations individually or select the multiple stations to create a composite coverage from the stations that we're interested in. So for here, call this a composite coverage. We'll press process. And here we can see the new coverage from our stations here. So at this stage, we're able to alter the palette. So rather than having a single value, we can create a number of discrete values and see the difference in signal level as we go further from our stations. So we can see this area here is not very well covered by this new transmitter 3, so it might be worth moving this transmitter. We can select move, maybe move it closer to the middle of the population. I'll just change our palette back. And now what we can do is see the combined coverage from the additional site as well here. So what we'll have to do is recalculate this path loss matrix. This time, just for speed, we'll go 1,000 points. And then we can see the composite coverage from all the stations here. So we can see the input from this station as well now. Okay. So there will be some iterations in identifying the coverage and the best site locations, antenna heights, antenna styles as well. And that can be modeled through various iterations, changing the parameters within the sites. So as we put the crosshair over the sites, we can get the object info and we can see the parameters and edit those parameters as well, rather than going back through the network page, which is quite handy. So the next thing we want to do is understand the interference that's happening within this system, within this single frequency network. So we can do that. We've got a specific function, which is the SFN interference map function. So as we click this, we'll have the ability to input our parameters. So it takes our threshold, and again, from the relevant documentation from the technology that you're using, the guard interval, useful signal length, and contributing length will be determined and specified. The various values that are usable for the different technologies, the different throughputs that you're requiring from your system, and the resiliency of your system as well to interference. So we'll try with the default parameters now and create the SFN map. So this is a map of carrier to over noise plus interference. So we can see the areas where the guard intervals and parameters that we've chosen, and the output in terms of our carrier to noise plus interference, carrier to noise plus interference, and how that changes over the area that we're interested in. So we can see here, we've got some red areas, we've got quite a weak signal, so that could fade out a lot easier. And then as it changes as we go through. So if we go back and redo this, we can change the parameters again, so we'll keep the same threshold. What we'll change is shorten the guard interval because everything's a bit closer together. We'll increase this and make our contributing length a bit bigger. So as we change the parameters, and again, based on the technology, we'll be able to use specific parameters. And now what we can see is we've removed the majority of the red areas. We still have some orange and the kind of teal coloured areas, but we can see an improvement within the network. And again, after more tweaking, more iterations, we can quickly build up a picture of suitable parameters to use within the network to get the coverage that we require and minimize the interference throughout the network. So once we're happy with this, what I'll show you now is have a look at some of the population covered functions. So the population covered will be based on our predictions. So we've got our prediction of the full number of sites, including the one across the water here. So we can see that the green area identified covers partially some of these sites. And what we want to do is really quantify that for use in reporting the number of population points, and also we're able to identify and quantify the percentage of the polygon or a number of polygons within our shapefile. So as I mentioned earlier, the vector files can be point data, line data for maybe road or high road, rail, or other linear networks, and vector polygon data. So this could break down a country within districts, so we can identify what percentage of a district polygon is covered. And this has other applications in terms of IoT network design as well. So first of all, we'll look at the covered vector polygon, and then we'll look at the covered population points. So for the vector polygon, we use the same method for both. I'll click on the polygons covered function. Then we'll select our vector that we're interested in. So for here, it's the Bristol boundary. We'll use the prediction that we calculated previously, put the threshold that we're interested in, press process. So that will return the percentage of that polygon that's been fully covered. So in this case, we can see we've got 28%, and any other information associated with that polygon will be stored within the output. That can be downloaded as a CSV for further analysis as well. The next thing we'll look at is using, again, the vector layers, this time just the population points. We'll use the same prediction, same threshold, and we'll be able to process this. What this will show us is for each individual point, we'll create a report of whether that population point is covered, and then the power received at that population point as well. So that can be quite important for, again, when we're reporting, if we want to look at various percentages of population points covered at specific power levels as well. Again, any other information associated with it. So this can be taken, the population data, from census information and from whatever other data sets that we have available as well. If we scroll down to the bottom of this data set, we can see we have the option of downloading to CSV or having it the file emailed to us as well. So from there we can identify and do further analysis, maybe in other tools as well that we're interested in looking at. So that's a very quick run through of some of the SFN technology, how we can import data, creating a network within SpectrumE, looking at the k-means algorithm as a way to identify suitable locations for placing our sites. Then we looked at the coverage maps and the SFN interference and how we can use that to minimize the interference within the network. And finally, we looked at the population covered functionality and how we can use census data, population points, and vector layers to understand the coverage within our design network. So again, broadcast is a wide subject, and we've covered relatively very little of it today, but hopefully we've been able to show some of the possibilities within the tool. And I'll pass over now if we've got any questions that have came through the presentation.
Thanks for that, Ross. That's great. Yeah, we have got some questions that have come through, and anyone that does have any questions, please drop them into that questions toolbar and I'll be able to put them to Ross now. First question, does the tool have the ability to model MFN?
MFN, yep. So part of, again, as I mentioned, broadcast is a wide subject, and what we've covered today is probably a slither of SFN technology. So we do have the ability to model multi-frequency networks, and again, it's just some similar functions and some different functions that we've created for modeling those types of networks as well, looking at interference between areas, and yeah, there's a variety of functions which again probably could be covered in a webinar itself.
That's lovely, thank you. I hope that answered your question, George. Yeah, that's great. Okay, next question. What format must vector data be in for importing? So that's the import of vector data. What format does it need to be in?
Yep. So for importing the vector data, we can import as either a shapefile or a KML file. So through the vector import toolbar, the projection has got to be WGS84, and certainly there's more details within the user guide of the how to import and the steps to take to import a vector layer as well. So hopefully that covers off that question for you.
Thank you, Ross. I hope that answered your question, Sunny. Thank you. Okay, another question. How are vector layers imported into Spectrum E?
Right, yep. So we can maybe just go back to the demo to quickly show how that's done. So again, within the tool, we'll be looking at the vector options. From here, we're able to change, so upload the vector file using the specific file type. Choose the file from here and press upload. It'll appear within our list of vector layers, and from here we're able to turn that vector layer on or off, change the color of it, and also we're able to change the size of the outline as well. So maybe if we want a thicker line for reporting, I just have to zoom back into that point. We're able to see a slightly thicker line. So that's how to import vector layers.
Okay, that's lovely. I hope that answered your question, Paul. Okay, next question from Quintin. Why was the elevation not populated in the transmission? Sorry, I'll start that one again. Why was the elevation not populated in the transmitter information table? Could this be auto-populated from the terrain data in use?
Right, yep. So on the elevation, so this field itself isn't taken into account through the coverage predictions. What Spectrum E will do is it will pull out the data from the terrain data set that's underlying and use that for the calculations. So to populate this field here, there is a way to automatically do that. So by highlighting the stations, have an option to update elevation here. If we click that, what that will do is that will pull in the data from the terrain model and place it into that elevation column there. So hopefully that answers the question in terms of partly why it wasn't populated and how to populate it as well. So again, that could be quite useful for reporting and exporting data.
Okay, hopefully that answers your question, Quintin. Okay, while we're waiting for more questions to come in, there are a couple of things. Okay, in the absence of any further questions, and we don't seem to have any more, I think we're going to call an end to today's event. Thank you everyone so much for joining us. Thank you, Ross, for presenting, and we look forward to you joining us at our next event. Thank you.